Hello everyone. Welcome to week 3 of the interactive sessions. So let us wait for a few minutes so that other people can join. Yeah, hi. Yeah, so I guess we can start. Good afternoon. So this week, the topic that was covered was backpropagation. So earlier in the last lecture or in the last session, I think we discussed about gradient descent, right? So how you initialize your weights and then you try to get to your optimal weights by doing gradient descent. So when you're doing gradient descent, you need to travel along the gradient. Now, how do you calculate the gradient? That is where this back propagation comes in. So yeah, which part would you like to, which part should I, do you want me to explain? So you can just, or if you have any other doubts, you can, uh, yeah, unmute yourself and ask. So gradient descent is basically your chain rule that you must have seen in your high school calculus. So yeah, yeah, yeah.
So,
I-
I had this one question regarding week two assignment, the 10th question.
Okay, let me
After looking at the solution, also, um, I was unable to understand.
okay,
Week
let me
two,
check.
yeah,
Mhm. Question number 10.
question number 10, yes. If I manually calculate the summation for say 0, 0, 0, 1, 1, 0, and 1, 1.
Hmm.
I don't know where I'm going wrong. Uh, every time, so if it is 0, 0, the answer is minus 2.
Hmm.
If it is 0, 1, the answer is minus 1. 1, 0, the answer is, I mean, if I just consider the first two.
Hmm.
Um, mm,
So
so for
yeah.
everything, I mean, the first one, 0, 0, I'm getting minus 2, which is less
Hmm.
than 0. The next 0, 1, it is minus 1, again less than 0. 1, 0, it's minus 3, again less than 0. 1, 1, minus 2, again less. So it is not getting fighter in either case.
So you are getting zeros in all of these, right?
No, I'm getting minus 2, minus 1, minus 3, minus 2. If I get 0 also
Hmm.
will get fired, no, greater than or equal to 0.
Yes.
So the second case, uh, because the way that problem is,
Okay, let me go through it.
yeah,
Give me a minute.
you can probably, like, if you can open that in your,
Hmm. Yeah, let me share the screen.
yeah. So it is supposed to, XOR means it's supposed to get fired uh,
So did
either if
you
it is,
add the bias?
yeah, that's how I'm getting,
Mhm.
after adding the bias only I'm getting this minus 2.
Okay.
So for 0, okay. So 0, 1 and 1, 0, it should get fired, right?
Hmm. Yeah, if these two are different, then you should get one.
Yeah.
Else, okay. Hmm. So the question is x1, x2, and then you have bias. Okay, so suppose I give an input of 1, 1,
Yeah, 1,
and
1. So
hmm,
it'll be
1.
1 into minus, because all
Hmm.
everywhere it is minus 1 and plus 1, the weights.
So each one will have uh, 1 into 1 plus 1 into 1, that is 2, and you have a bias. So yeah, you have a bias of minus
No,
2, so
1
1,
in
1.
minus 1. No, so all of them are uh, the one weight is for all.
Oh,
One
acha,
weight is
acha. Yeah, yeah, yeah.
minus 1 and one weight is plus 1.
Oh, acha, I
So
missed
when
that.
we
Okay. Hmm.
so when we take 1, 1, it Only -2 remains.
Yes, yes. Mm. So when we have 1, 1, each one will have 1 minus 1 plus 1 into 1. 0 minus 2, get minus 2. And okay, suppose you have 1, 0. Oh, sorry.
1 0, I'm getting -3 as the answer.
Mm. No, one thing I'm not getting here. It's okay. So what does this mean that each hidden neuron has 1, 1 or minus 1, 1?
Sorry, sir?
What does this mean when they say that each hidden unit has 1, 1 or minus 1, 1?
I did not understand that.
Mm.
I was just simply going with the whatever the question says, and then this is if the weights are this, and for
Mhm.
x1 and x2, I gave 0 0 0 1, and I was not able to get.
So can anyone, did anyone get it?
We can just probably mark it, and then next class also you can check, is there anything.
So actually, this is not clear. What do they mean by these things having
Yeah, yeah, that
one?
from day one only I never understood what is the
Mm,
meaning of that in this particular question. So I thought maybe so. I didn't
yeah,
feel
yeah, yeah.
anything correct, so I just marked it as false, and then it turned out to be true. Uh,
Oh,
so I thought somewhere some understanding issue. We can just move on to the next question. Shall I ask? We can. I
uh,
mean, you can just mark this question.
so let us say 5 minutes, and then we can go on to that. So I need to understand what does this hidden
Yeah,
neuron
yeah.
mean?
At first, I thought like they're saying that after multiplying this is the. I don't know what is the answer. No, that is not the thing.
So did anyone? So all of you must have gone through this. Did anyone understand what does this mean? Okay, let us go on to the next one.
Yeah, you can just mark it.
Mhm.
Uh,
So I have to
next
think
one.
about it. Hmm.
Yeah, what exactly? is there. If you see question number, the tower question, yeah, question number three,
Three. Okay.
and they're saying that 100, we need 100 tower functions.
Hmm.
So we on that part, I understood you with two neurons, you will get
One tower function.
one tower function. So
Hmm.
my understanding was how I calculated was I with two neurons I got one tower function, and I considered that as uh, and then when you aggregate of all those uh, three layer I made it, so I
Hmm.
was unsure, like, so instead of 201, initially I marked it as 201, and then
Hmm.
I thought like, no, 2 and then there will be some there will be one layer of all these uh, tower
Aggregation.
functions,
Hmm.
and then when you aggregate together, I kind of didn't understand, so I marked 50 also,
Hmm.
three layer. I was not very sure,
Hmm.
so I marked it as 251. And if you
Hmm.
look at the answer, 201, so uh, I'm still, I mean, I get it, but
Uh-huh.
I'm not sure, like, whether I should aggregate, I should make it as a three layer thing, or just one was, I'm not like 100% sure.
Hmm. So it will be
So
no,
it
it
will
will be
be only
something like
always two layers only.
huh. So you will have 200 neurons here,
Yeah, when the
right?
200 neuron, okay.
So you'll have 200 neurons here and one additional neuron here to add all of this together.
So when I'm adding, so this two
Huh.
will
This
get,
huh.
yeah, I made it a three layer. That
Yeah.
was the
So
mistake.
this I think I showed you a demo
Overthinking.
last time, right?
Yeah,
So
yeah, yeah.
uh-huh. So it comes from there. So you need
Mm,
200 here to get 100 tower functions,
mm.
and this will aggregate everything.
I thought like we'll get by adding two, there is one layer of 50 neurons, and then after that they aggregate.
Acha.
Overthinking.
Uh-huh. No, no.
Okay.
Okay.
Uh, Six.
Six.
Yeah, sixth question.
Hmm.
If you can verify, because in I understand, because what I did is like online, I went and checked a sigmoid
Hmm.
plotter,
Uh,
and it is showing like that only. It is difficult for me to sit and plot and keep changing these values. So I went to in that plotter only and checked. But in our
oh.
video, is there anything wrong in our video? Video says that, I mean, if you actually run the video, you can see
Hmm.
that mm, uh, as b is increasing, it is
Hmm.
shifting towards right actually. You can see the graph going, uh,
Okay.
shifting to right. So if you
Hmm.
can just check whether the, I know the correct answer, what the correct answer is, I know, but
Hmm.
in that video, was there any problem in the video?
Okay.
So that
Which one? I have to check.
sixth question, yeah,
Uh-huh.
I mean, there were people were asking in the discussion also.
Uh-huh.
Finally, I didn't see any final answer. Is there anything wrong in the video? One, I mean, during this time only, sir
Hmm.
was saying that, Mitesh sir was saying that to do some correction, this should not happen. And but at the towards the end, also it was wrong. So, is there something wrong in the video only? The next time when we see, at least we should be,
Okay.
if that can be at
So,
least fixed,
hmm.
because afterwards when we go and recheck, we would have forgotten all these things,
Hmm.
so if that can, if there is an error, if that can be fixed.
Okay, I have not. I forgot
You
about
can,
the. I
yeah.
will slides. So did they reply there?
I could not see. I mean, I, I, I didn't think there is
Mhm.
somewhere. I think I saw somebody asking.
Mhm. But this solution is clear, I guess, because once you change
Yeah,
B,
but in that class, somehow that thing was stuck in my mind. In
oh,
the in the class, okay, when it is increasing, when you increase the value of b, it is sliding towards. And I mean, that was just stuck, and then I didn't try to actually do it.
oh, uh-huh,
Uh, so I was finding it a bit difficult to actually sit and do
oh,
when you're changing these, so it was easier to use a plotter.
mhm.
That's what I was also wondering, like in the exam we will not be having all these access
Oh,
to plotters.
yeah, yeah.
uh,
So in exam, you can do one thing like you can put some extremely large value and see. Means then it becomes
mm,
easy. If you put 100, you can put minus 100.
mm, uh, yeah, that's
So there was
mm,
this, yeah, plotter where they're just learning the W's and B's.
mm.
And so,
Can you just take that thing now, increasing the value w and b?
yeah, let me share this
Yeah, if
screen.
you can show it without any, if we
Mhm.
can take some values and
This is visible, right?
yeah.
Okay. So here, as you can see, they're learning the B's, and the B's are becoming progressively more negative. And so,
Mm.
okay, so as the B becomes negative, there is a shift towards right. So this is B0, this is minus 0.95, and at minus 2, it moves towards the right, right?
B should move actually towards left as it is
Mm,
increasing. In this only, if you
mm,
just after not the slide, if you in this video, maybe after
mm.
a minute or so, this thing, what I'm saying,
Hello?
they actually use
Yeah, actually, there's a network issue. I'm not able to get you. I think there is a network issue. I'm not able to get you. Am I audible? Can anyone
Yeah.
confirm? Because, yeah, I'm not able to hear anything. Hello? Yeah, can anyone else confirm if I'm audible or is there a network issue?
I can hear.
Okay, so I think Lalita, you have a network issue. It is not clear what you're saying. Yeah, thank you.
Yeah. Yes. Yes.
Hmm.
can hear you. Can you hear me? Okay.
So meanwhile, can I ask one question here?
Yeah, sure, sure.
So these are three axes, right? X, Y, and Z axis where we are plotting error.
Yes.
Okay. So these are the loss values or what these values indicate?
Oh, so this one here, this is the loss, this error. So you have X, Y, and Z. So these W and B are the parameters that you'll be learning. And based on these two parameters, you'll get an error.
Okay.
Is that clear?
Yeah.
Hmm. So for this is an easy case, but for others, it will be a very, there will be a lot of X's and D dimension X's. So, but for visualization, you can just visualize in 3D. So we have one W, one P, and the error.
Okay. So the error is plotted as a Y axis, right? X.
Yes,
Okay.
yeah, you can think the error is a function of both W and P. So each parameter will be one axis, and the Y will be the loss will be the other axis.
So it may go in the negative also, right? So
No, no, loss cannot go to negative because see, loss is how many times you are correctly predicting something. So if those two things are not equal, then you have a loss. But once everything is equal, you can say that the loss is zero. So the
yeah, but
loss,
it is plotted this 0, then minus 0.5, minus 1.
yeah,
But there
but
is no value. Okay, got it. I mean,
uh,
there are values only for positive. There are
yes,
no values. But weights and biases can go in positives and negatives both, isn't
yes,
it?
weights and biases can take any value.
Okay. And in the this legend
Mm-hmm.
in the bottom,
Hmm.
it starts from 0.08 till 0.64.
Oh, this is just a description of how you can interpret
Okay.
this.
Blue
So
color,
more
right?
red means, yeah, more red means it is more large.
Okay, got it.
Yeah, hello, Lalita. Can you hear me now?
Yeah.
Yeah,
Yes,
yeah.
yes.
So there was some
Yeah.
disruption on your end, I guess. Yeah. So can
Yeah,
you?
yeah, yeah. I got disconnected.
Uh,
Yeah, can you just zoom in because that
okay.
legend of that graph is not seen.
Yeah.
Which one is the one with?
Yeah. So it is something like this. This one is for beta zero, and if you go beta decreases, so this is the smallest beta minus 2.28, and this curve goes more towards the right.
Okay, as B decreases, it is going towards right. Yeah.
So in the correct answer is as you increase B, you go towards the negative infinity. So you go in this direction.
Yes. Yeah, yeah.
So that is what they say in
Yes.
the solution.
Okay.
What is the difference in this plot and the other plot? I mean, in other
Uh,
plot they plotted in 3 dimension, but here it is 2 dimension.
so here they are plotting only this logistic function. If you change, so here y is your function of x. So if you change w and b for what is the sigma x that you get. So this is your sigma x. And here they are plotting the loss. Here they are plotting the loss. So that means this is the, yeah, this thing here is the output of your neural network. What is the output that you give? And once you get an output, then you can compute the loss, right? So you get some
Okay.
output y, but you know that there is some true value y dash. So the loss between y and y dash is the error. So here they are plotting this error. What is the difference between the output that you get and what is the true output? So they are plotting that here. This is just the output of the network. Is that clear?
Not exactly. So you are
Hmm.
saying that the predicted value, the first one is for the output of the logistic function, right?
Yes,
First
yes.
one is output of logistic function, but this is the other plot is the output of the overall neural network function.
No, no. This is not the output. So suppose, so let us take this example. Say this red curve here, right? So for say W 0.5 and B 0, your output is something like this. So let us say when your output is or input is X, your input is X, you get an output of something, I think 0.5 or something, let us say. But now your network is outputting 0.5, and suppose the correct answer is 1. So the error is 1 minus 0.5, right? So that error is plotted here. That error is plotted here because for say, so this was for example when W was 0.5 and B was 0. So if you go here, so W is 0.5, so somewhere around here, and B is 0. So somewhere along this line, at this intersection point. So what is the loss that you get?
Okay,
Uh,
good.
you got it?
This is the error plot, and the first one is the output of
Output.
the neural network. Okay,
Yes.
got it.
Yeah. Coming back to question 10.
So to implement neural network without these TensorFlow or PyTorch libraries, which we have manually doing, like we did pseudocode in week 3.
Yes.
You have to implement that in Python. Uh,
Yes.
you have to manually give the weights for each layer if we are not doing this.
Oh,
So
okay. So, that is good question. Okay. Shit. Hold on.
because the sizes are different, you can't have it in one array.
Mm-hmm. Yeah. Okay. So if you are manually computing or creating, constructing a neural network, So uh, because in neural networks you do not always initialize your w's to zeros,
Yeah.
because if you initialize to zeros you will get everything to be the same.
Mm.
So what you do is you just say that okay, my weights are something from normal distribution.
No,
So
but
there is
what
so
my thing was doubt
hmm,
was whatever we are initializing it,
hmm,
but we have to manually initialize for every layer separately. Okay,
yes, yes,
W0 is my for initial
uh,
first layer one before layer one, and
yes,
then next. So if I have three layers or four layers, I'll have to
mm,
manually do it if
yes,
when I'm doing without these libraries.
yes. So
Okay.
you can use this NumPy library. You must be aware of it, and you define everything to be in the form of a vector. So
Yeah,
let us, let us say this is my input layer, layer 0. This is
your
my layer 1.
screen is not shared.
So, Shruti sir, again I cannot see the screen.
Oh, is it
Yeah,
not scared?
yeah,
Shared?
it's not shared yet.
Oh, is it visible now?
No,
Mm, let me reconnect. Yeah, now?
I cannot see that. Only I can see the name Shruti Moidas, but I cannot see the content.
Okay. Mm, because it is showing here in my screen. Yeah.
Maybe I think if you rejoin it, maybe it should resolve it.
I resigned. Let me check. Yeah, this has so much issues. Yeah, how about now?
no, the screen is still not shown.
Oh, but I think some of you are able to see.
Somebody, yeah, someone is able to see. I can't see.
Can you reconnect?
No, even I cannot see the screen.
Oh, maybe there is some connectivity issue because some people are able to see.
Okay, I'll try doing that.
Yeah, can you please reconnect?
Okay, I can also.
Yeah, yeah. Yes, it is visible. Hmm.
Yeah, now we can see.
Yeah, now it's
Yeah,
coming.
Yeah.
Yeah, is this visible? I am writing some things.
Yes.
Yeah. Yeah, I'm using Teams because we have to record this session and Google Meet does not allow me to record more than 40 minutes. So that is why I'm using Teams. Else Google
you
is
can
better for
continue.
this
Yeah.
anyway. Okay. So suppose I have this network.
Yeah.
My layer, this is my input layer. I have 3 neurons here. I have
Mm.
4 neurons in the first hidden layer, 2 neurons here, and 1 neuron as the output layer. So we know that these will be connected to this. So you see there are 3 neurons here and it will be connected to 4 neurons. So what will be the total
12,
number of weights here?
12
12,
weights.
right? And so if I am to write this as a matrix, what should be the size of the matrix?
It'll be 4 by 3.
4 by 3, right?
Yeah.
So everybody is able to get this, right? Because understanding this will make everything easier. So in case it is not clear, so let us say that this is x1, x2, x3, and this is a w11, w12, and so on. And finally, we'll have something like w33. So this weight matrix is basically 4 cross 3. So w11, w12, w13, w14, and so on. We have w31 and w34. So we can put all of these weights in a matrix and then we get this w4 by 3. So if you are creating a neural network with say NumPy library, which is very basic, you do not need to go into any of these advanced things. So for simple
np
neural
dot
network,
array
uh-huh,
np dot array, right?
yeah, some np.array. So it has a lot of functions,
Okay.
np.array, np.matrix. So how
Mm-hmm.
do you initialize these weights? So there is something called np dot random dot
Random dot, yeah.
uh, rand
Rand.
n.
Yeah.
So now in random, what you do is you know that your weight matrix is 4 by 3. So you return a matrix of size 4 by 3. And then what it does is each of these will be a no, random variable drawn from a
A
normal
random float.
distribution.
Yeah. Yeah.
Yeah.
So this I
So
got the on my doubt was like now
mm,
I in or the all the entire matrix I have to say I'll call it as W1 or W0 and I'll
yes,
have this and then again I'll have to do for W2 and W3. So for learning
yes,
sake we'll have to uh, I mean actually W1, W2, W3 I'll have to hard code it as this is
yes,
the
right, right. So
values.
yeah,
I was wondering, like, if I have to, in our lectures, we were referring, say, first layer W11 of first layer. So
uh,
it was like W111.
yes,
So that I will not be able to do here. It was a doubt because in my same array I cannot have multiple in the same array. So if I have to reference the uh,
you need this.
W11 of the first layer, I cannot do it like that.
Okay.
So I was just thinking, then it'll be too much of code to do it. So the
Yeah.
entire, I
mm,
was wondering like how that back. Anyway, I'll check it again a little bit. I will do,
yeah.
and
I
then
mean,
in probably
it,
next session I'll ask out.
yeah, yeah. I think it can be done, but yeah, you'll have to go into a bit more depth
Yeah.
into this. So
Yes.
you have to
Yes.
look
Yes.
at each of these neurons, each of these weights.
Yeah. Yeah.
Hmm.
I'll do that. It's okay.
Yeah, try
Thank
it out.
you.
So it's a
Yeah.
good
Yeah. Sure.
exercise to try these out in
Yeah,
NumPy.
there is last time when you said I had not done that gradient descent. I
Uh,
actually did. It was a very good learning
yeah,
and
yeah, yeah.
could actually see it, though it was a very tiny one, but it did make a lot of difference in actually doing it.
Yes.
Yeah, thank you so much.
Yes. Yeah, yeah. Yeah, for question number 10, if anybody solved it, maybe you can share. I'm still not able to get what do they mean by having this hidden neuron as values having 1, 1, 1, 1, minus 1. Yeah, any other question? Or you want me to explain uh, regarding this last lecture or the previous lectures?
So in last lecture, there was a lot was explained in entropy and was
Ah,
explained very beautifully. But there's no questions, not much in that assignment, week 3 assignment.
mm,
In backpropagation, absolutely zero question. So
o-
some questions would be nice.
okay. So there are questions on number of parameters, sizes of this. Yeah.
Yeah, backpropagation, there is no question.
Okay. So I think they have not given this because yeah, for big networks it is a bit tiring to compute the gradient of each and every neuron.
Yeah.
Maybe that is
But the
why.
small network, small things, 3
Mm-hmm.
3 or something, but when we actually do it, it is nice. And when you see the result, okay,
Right.
my answer is correct or not, it gives some confidence.
Yeah. So let me see. I can.
The lectures are very beautiful. It's very nice.
Yeah, the
Even your
explanations are
sessions are
good.
all you're explaining very slowly and nicely. It's very nice.
Uh-huh. Yeah, so the thing with backpropagation is even if I go to do an example now, it has a lot of numericals. Like you have to do a square of a very small number, then it becomes difficult to that.
Okay.
So let me share my this screen. Is this visible? Is this visible? Okay.
No,
Oh,
whiteboard is not visible again.
not the whiteboard. I am sharing a web page.
No, nothing.
Okay. How about now?
No, I don't know
Oh,
about others if anyone
I
else
guess
is able
some,
to.
yeah, some people are able to see this. So again, you must reconnect, I think.
Oh, okay, I'll try. Yeah, I can see now.
Yeah, it's visible, right? Okay.
Yeah.
So we have a small, okay, we're small network here.
3 to 5 ఉంటుంది కదా అది ఓపెన్ చేశాను ఏం జరుగుతుందో చూద్దామని
A little bit, can
Mhm. Is this visible? So we have a
yeah,
simple two-layer network. So these greens are your input neurons. So I'm taking this from this website, mathmeasure.com. And then there is a hidden layer and there are the output weights, and you have some sets of biases here. And now let us say we initialize it to some weights, say W1 is 0.15, W2 is 0.20, and so on. And using this, you get some output here. And let us say you're using mean squared error type of thing. So mean squared error is the difference between your output and difference between a true value and the square of that. And you sum over all of the data points that you have. So, okay. So there is this net H1. So net H1 is this one. What is the output that you get at H1? So that will be uh, your 0.05 times this weight and the 0.25 times this weight. And then there is a bias of 0.35.
this is without any activation, just
This is without any activation. This is a
a
simple,
summation,
yeah,
simple summation.
yeah, right. So that is what they do here, and they get something like 0.0.3775. So in the lectures, they have, so each hidden neuron can be divided into two parts, a partition. Like you
Yeah.
can have a pre-activation and an activation. So
Mhm.
now without any activation, this is what you get, pre-activation of 0.3775. And now what we do, we use a logistic function. So that is basically you plug in your this pre-activation that you get, and you get a logistic function, a logistic output of 0.59. So logistic gives you an output between 0 and 1. So that is what you get here. Now, similarly, you do the same calculation for H2 here, which is 0.05 into 0.25 and 0.10 into zero point 0.3 plus this bias. And then you do the logistic output on all of that. Now, coming to O1. So this O1 will depend on your H1, whatever output or whatever activation that you have on H1 and whatever activation you have on H2. So that is what we do. So you out W5 times out H1 and W6 times out H2 plus some bias that they have. And again, the activation here is the logistic function, and that is what we get, some 0.75.
Hmm.
And similarly, you do this for the second what is O2. So
Hmm.
here now, so if you go here, so at out O1 you are getting 0.75, and here you are getting 0.07, but your ground truth was 0.01 and 0.99. So instead of 0.01, you're getting something like 0.75, and instead of 0.99, you're getting something like 0.77. So the difference between this 0.01 and the 0.07 that you are getting, so that is the loss that you have. So we calculate the loss. So for simplicity, we are taking this MAC type of loss. But if it was a probabilistic output, so you could take the softmax activation and a cross entropy loss. So this is, so even that is easier, but yeah, for now, let us say we're taking this squared error function, and this is the loss that you get. So this is your output on
Sorry, I
O1.
missed that. What is the probabilistic output? I didn't get that.
Okay, so if your output is a set of probabilities, say
Okay.
you're doing a classification thing, you give an image, and you have to classify whether that image contains a cat or dog or a monkey. So you give your output will be a probability, like what is the probability of it being a cat, what is the probability of it being a dog or a
Okay.
monkey.
Uh-huh.
Yeah. And suppose it is a image of a monkey, your probability of monkey should be the highest. And if it is not, so your loss will depend on the difference of your probability that you get and the true probability, which is say 0, 0, 1, where monkey has the probability of 1. And then you do a cross entropy loss and you back propagate it. So here they are not using cross entropy, they are just using this MSC, squared error type of loss. And this is what they get. On O1 they have a loss of this much, and O2 they have a loss of this much. So total loss is summation of these two losses. So now you have your weights, you have your activations, you have your activation functions, and now you have your loss. Now because loss is of course not zero, your next step is to do gradient descent to learn the weights. But before doing gradient descent, you need the gradients, right? And how do you get the gradients? You calculate the, you use the backpropagation algorithm to calculate the gradients. So let us start. So, okay, uh, there should have been two images, but okay. So so for this one, so this output is dependent on this O1, and O1 is dependent on W5. So W5 depends on H1, H1 depends on the pre-activation before H1, and that depends on W1. So hopefully you're trying, you get this dependency. So that is how we will calculate this back propagation. So if you go here, so this is the E total that they have. Yeah, this is E total that they have. And now they want to compute what is the change in loss with respect to W5. So how does the loss depend on W5? So this is how. So this is the loss that you have here on the right hand side. Hopefully you're able to see my cursor. So this loss depends on output of O1. This output O1 depends on this pre-activation, and then this depends on W5. So there is this three level of dependency. So that is how you write this back propagation, this chain rule. So this net O1 is your output. It depend. Okay, sorry. This E total is your loss. It depends on out O1, which is this. Then out O1 depends on net O1, which is the pre-activation, and this net O1 depends on W5. So this is a chain rule that you give, and this as a whole gives how much does W5 influence your loss. So that is how we calculate all of this. And then yeah, we do these computations. You get, so here what are the parameters that you have? So these are your parameters, right? W1, W2, W3, W4 up to W8, and then B1, B2. So total there are 10 parameters. So you will need the loss or gradients with respect to each of these parameters, because you need to update all of the 10 parameters. So you need a loss, a derivative of the loss with respect to W1, with respect to W2, and so on up to B1 and B2. So you need 10 derivatives. So that is what we need to compute for all of these parameters. So then there is okay, there are these details of, so for each activation function there will be a specific derivative that you require. And then once you have all of this, you put all of this together. So here they have just shown for W5. So you put all of this together in a big vector. So vector will be of size 10 because you have 10 parameters. And now that is your grade of L with respect to W. So now when we are doing gradient descent, so gradient descent is Wt plus 1 equal to Wt minus some eta times this gradient. And this gradient will be a 10-dimensional vector. And then you subtract this and you get a new set of outputs. And you continue doing this till you get, say, loss of 0 or something you're satisfied about. So this gives a small, not that small, even for this small network you need a lot of calculations. So yeah, I'll share this link, maybe you can work through this example. Yeah, hope this is clear.
Yeah, you can send this link.
Yeah, share this link, you can work this out. So because this derivation is very uh, very complicated, so these libraries, PyTorch or TensorFlow, they have something called autograde. So autograde, basically you write your code in terms of their library. Say instead of doing, say, a plus b, you just call pytorch.sum. Instead of doing multiply a minus a times b, you'd say pytorch.multiply, something like that. And then their library automatically recognizes what is the backpropagation that you need to do. So they maintain all of the variables that require a gradient, and then they automatically compute this backpropagation. You don't have to manually write it there. So that is called an autograde engine. But yeah, uh, for understanding, it is good to write it out. Also, these things are very complicated. So if you want to make it faster, you should try to write it in terms of matrices and vectors, because those are faster to compute than going element wise. So NumPy allows that. So let me show you one more thing.
So one question I have.
Uh,
So is there any specific reason that they use this chain rule here? Why they derive the values through chain rule?
oh, so the chain rule comes naturally because, see, what are you trying to do? In gradient descent, you are trying to update your weights, right? You're trying to update your weights so that the loss becomes 0. So how do you do that? So now you must understand how does the loss depend on each of your weight. So if we go back, yeah, go back here, let us see. So suppose you are interested in updating your parameter W3. So in gradient descent, you update all of your parameters. So suppose you are updating your parameter W3 as shown here.
Okay.
Uh, so how do you know that how much does W3 has a effect on the loss? So loss is not directly connected to W3, right? Because loss will be connected to O2, O2 will be connected to, say, H1, and for via H1 you are connected to H3. So in the language of differentiation, if you write this out, say uh, your loss is a function of O2. Now O2 is a function of H1. So if you write this as f of some g of O2, and again your H1 is a function of W3. So it is like a function of a function of a function, something like that. So if you
Okay.
go to derivatives, how do you compute the derivative of a function of a function of a function? You do chain rule, right? Say suppose I give you what is the derivative of say cos of x square. So first what will you do? You do derivative of cos of x square with respect to x square, and then you do
Hmm.
then you do derivative of x square with respect to x. So there is this chain dependency because cos of x square does not depend directly on x. Cos of x square depends on x square, and x square depends on x. So this is similar to that. You
Okay.
want to see how much dependency is there on each of these parameters.
Okay. Got it. Thank you.
So let me show you. So if you're writing a code in PyTorch in the future, it is very easy. If you know Python, you can learn PyTorch, and they also have tutorial on their website. So yeah, so you have some type of loss, and whenever you are training a neural network, you just you don't have to say compute the derivative of this, compute the derivative of this. You just say loss dot backward. So this loss, okay, loss dot backward, it computes all of the derivatives that are required automatically. You don't have to do anything at all. And then you use some optimizers. Say here they are using something called an SGD. So like you are using gradient descent. So let us say optim is gradient descent, and this optimed of step is your gradient descent update. Say wt plus 1 equal to wt minus eta times your gradient. So these three lines are what is required to you. I mean, what you need to write in PyTorch. You just call dot backward, and then you call optimizer dot step. That is what is needed. So whenever you are creating, right now I mentioned, right, you have these parameters W and B. So how do you know that the W and B, the parameter, I mean the gradients for W and B will be calculated? So in PyTorch, if you are creating parameters, say A and B, you just say requires grade equal to true. So when you give this argument that requires grade equal to true, the PyTorch library will automatically say that okay, I need to compute the gradients of this. So when you call dot backward, it will try to compute the gradient with respect to say A. It computes the gradient with respect to B, and it stores all of these parameters. So that is just a basic thing. So let us say you have this function here. Hopefully it is visible. Is it visible?
Yeah, it
Yes.
is.
Yes.
Yeah. So suppose you have this function, say q. Forget about loss functions or anything. Just say you have some function q, and suppose this is your loss function, and this q depends on these variables a and b. Now here you define that a and b requires some gradient, right? Oh, yeah. Here you define that a and b requires gradient. So it will keep in mind that okay, these are my parameters, and you need to compute the back propagation with respect to this. So this is how you define your q. And now automatically when you call dot backward on q, it will automatically do this computation. So derivative of q with respect to a and b, and then you can access this. You can just say that a dot grad, what is the gradient of a, b dot grad, what is the gradient of b, and then you can do, once you do optimizer dot step, they have not shown it here, it will just do the gradient descent update by using these gradients. So this is how everything happens in PyTorch. And okay, so how that happens is because here we are doing a basic multiplication, right? 9a square, 9b square. So they have functions written for this, say multiplication backward. What is the backward back propagation or derivative for multiplication? What is the derivative for powers and so on? So they have all of this written here. So hope that is somewhat clear. You can go to the PyTorch website and start reading through this. It may seem daunting, but yeah, if you work on it, I think it should be fine. Yeah, any more questions? Yeah, any more questions? Any other topic you'd like to discuss? Yeah, for question number 10 on assignment 2, uh, so they are asking about, they're saying that they have a network which has 4 hidden neurons, but the statement that they're saying is a hidden layer with 2 neurons is sufficient to implement. So when that statement is true, I don't know how it depends on the statement that uh, this neural network that they have given. So yeah, maybe someone can ask this question in the discussions. I'm not sure what is the meaning of this question itself.
So in this derivation,
Yes.
derivation when we are doing a gradient of loss with respect to pre-activation AI,
Can you say which slide? Or
which yes, this is in gradient for hidden layers. That is a
okay,
uh, video.
okay. So slide number,
So light number.
it should be in the bottom right corner.
Okay, I have not.
I don't have the video open actually. That's why I have the
Yeah,
slide.
yeah, yeah. Okay, I'll take some time. I'll just let me just download that. I'm just downloading it.
So these slides are also available in that reading
Yeah,
one.
that only I was downloading
Oh,
that some English that. I usually write down everything in my
uh,
notebook, but I did not. Next time, I'll I'll write the slide number.
oh.
Okay, page 278, slide number. Yeah, here it is not slide number, it is like page wise.
278.
Yeah,
Lecture 4, right?
lecture.
So on
It
the
is
bottom, there's a pen.
page 283, sorry. Lecture 4, yeah, bottom it is
Uh,
written lecture.
283,
It's,
yeah.
yeah. The final answer is given as gradient of loss with respect to AI. You have an Hadamard product. I had this because,
Okay.
yeah, I wanted to see why here it's written AIK, YK. It will be only in the last layer, so not for all layers. So,
Oh, so you are in the gradient descent algorithm, right?
yeah,
Backpropagation algorithm.
back propagation when you are calculating gradient with respect to uh,
Layers below.
yeah, no grade. Yeah, this is that pre-activation gradient with respect to
Uh-huh.
in that
Okay.
just one previous if you just the final that underlined is the final one. Before
Uh,
that, if you just see eh, here, I did not understand why in that last one after that Hadamard product is written why K is there because there are it is a bit confusing whether K is for
K is for the
AI1,
layers.
AI2, EIN is there. See, if you see AI1, I2, I2 in the previous, on top, if you see,
Uh,
there's a vector gradient with respect to AI is written as um, uh, you're doing a partial derivative of loss L theta with respect to A, A AI1, AI2, like that, AIN for each. Uh, and then after that, it is written AIK. That I did not understand. Everywhere it is AIN, and then it became AIK. I don't know if it's like a mistake or I have not understood.
So this one you are talking about, right?
No, wait. I did not. Let me go to Teams now. Oh, I again can't see your screen.
Oh,
Oh my God.
yeah. Sorry about that. I don't know why this problem is coming.
Oh, today only, I don't know. I've never faced
Mhm.
any issue. Let me just leave and come back.
Yeah.
I can see now.
Yeah.
So
So is this what you're talking
you
about?
can, yeah, this is only I'm talking.
Ah. So yeah, this seems correct, right? Yeah.
And then why it is mentioned as AIK here? AI1, if you can see that you're doing the G prime,
Yes.
G prime of A I1, G prime of A I2, like
Mm.
that A I N.
Yes.
And then when they're saying that, you can see that Hadamard product symbol, and
Yeah.
then they have written, yeah, why they have written like that AIK there?
Oh, AIK means it is for any general K. So K goes from 1 to N.
Okay, goes to 1 to n.
Yeah, it
It
is
is,
just a
that's
general
what is
term.
like always. I
Uh,
thought is it that there, because K is the term that is was usually used for, there are K classes in that last
yes, yes.
layer.
Yeah,
So
yeah. So I
okay.
think, yeah, they should have mentioned something like, so K is just a general term. It can be any
Okay.
one of these thing. So here also, that's why they have this one.
Yeah, rest the previous step and all everywhere. That K is different only.
Yeah, this is different.
That is what it was
That's
a bit
confusing. Yes.
confusing. I mean, yeah,
Uh,
that should be like at least that as a feedback. I think I will write. Uh, it
yeah, yeah.
There are two, yeah, because in your pseudo algorithm the K is different, and
Yes.
until the derivation the K was different. So
Uh,
it becomes as it is, the derivation is so. I mean,
yes,
you have to
notations
concentrate
are
on the I's and K's
not
and
clear.
all.
Hmm.
Yes. So yeah, that was, I was trying to write some other instead of K, but I messed it up. So I thought like, okay, never
Yeah,
mind.
yeah. It should be, yeah.
Okay.
So actually, I think the dimension of the output, it will not come here anyway, I think, because so somewhere it will come with respect to parameters layer below. Yeah, I think number of classes does not matter here, because your loss, the dimension of the loss will take care of.
Yeah.
Mm.
Mm. This is what I was like saying, that in that pseudo code, if they're saying that mm, for the first layer you do wk equals to uh, like that.
Mm.
I mean, that kind of an indexing. It is difficult to have this kind of an indexing. At least I
Yes.
was finding it difficult to have this indexing uh, for that I
Uh,
can do one wk provided everything is in one array.
yes.
Otherwise, to reference that w, so that particular w, how to reference? Okay, let me
Mm.
do some homework on that. Okay, thank you, sir.
Okay, thank you. Yeah, so if there are any no more questions, you may leave. I'll be available till 5. So we'll meet again next Saturday. Thank you.
Thank you, sir. Bye-bye.
Thank you.
Sir, at the end, what's the answer of 10th question, sir?
Excuse me. 10th question of week 2. Yeah, so
Yes, sir.
so that question that we're asking was whether if you have uh, a neural network of 2 neurons, is it enough to classify a XOR function or implement a XOR function? And that is true, right? Because we saw that one neuron or with one perceptron you can draw a linear classifier, but XOR requires you to learn two classifiers or two lines which can differentiate between the points. So if you have two neurons, you can easily implement a XOR function. So that is true. So I'm not able to see what is the connection between that question and the neural network that they have shown. I think it does not matter because the question that they're asking is about the statement, whether you can uh, implement XOR using this two-layer neural network, and that is true.
Sir, in the neural network for one case, it is the resulting 4, sir. After removing the bias, the answer is 2. But how since it is 2, the function will be activated, no, sir. X1
Come
equal
again.
to 1, X2 equal to 1.
Yeah. Come
Sir,
again.
for the case X1 equal to 1, X2 equal to 1,
Yes.
the resultant bias is 4, sir.
Bias is given
Total
as
aggregation of
-2.
the all weights. Yes, sir. Sorry, sir. Not bias. It's the aggregation is 4, sir.
Need not be because this reds are weights are -1, so -1 and 1, and these blue weights are +1. So we have to multiply your x1 with -1, x2 with +1. But the question that they're asking is not about this neural network at all. The question is about two neurons. Is it sufficient to implement XOR? So with two neurons, it is sufficient to implement XOR. With four neurons, it is also, because with two neurons, if it is possible, with four neurons also it is possible. So that is why it is
Yes, sir.
true.
Yes.
Yeah, you were saying something?
Nothing, sir.
Okay.